Everything that you've been doing so far in high school has been in two space, Cartesian, the x, y coordinate, Cartesian plane, all the way back probably to even, I don't know if you do it in grade 7, but I think you talk about it a little bit in grade 8 kind of thing. So you've been working with, you know, the XY plane for a long time, and this is the first time that you're going to see it in 3 dimensions. And almost everything we do today is very repetitive. And like, I'm going to teach you almost nothing today. It's exactly what you would expect it to be for obvious reasons when we go over everything. But everything we've done up till now, we've done in 2 space. We're just going to redo all of it in 3 space. There's a few questions that I think some of them at least have been in the practice over the last few days. So if you haven't done the practice, they will be new to you, and they're just asking questions kind of backwards. So it's something that you need to be able to do. So we're going to do some examples of those together, which will be good. But almost everything we do is really, really not hard, not new, not particularly interesting. Except that it's 3 space, and what we're doing for the rest of this unit and a lot of the next unit will be in 3 space. So we're going to see a lot more of this. In the next unit, which is called lines and planes, very interesting extensions, what happens when you move into 3 space. It is very different from 2 space, but we'll see that in the next unit. As I said, you've been working in 2 space for a long time, and you think back to something that a long time ago, let's go even further back, that was difficult, like multiplying integers, negative numbers, or just multiplying in general. When you first learn about it, it's very difficult. But now you've been working with that stuff for years and years and years, and you don't even think about it. Like when you first learned how to multiply negative numbers, you had to memorize the rules because it didn't make sense. A negative times a positive gives you a negative. You don't think about that anymore. You just know that that's the case. And I think you can imagine if you were working with vectors for the next 5 years or 10 years, if you were doing it in the program that you're going to study in your future, or even in your career, all of the stuff we're doing right now would become so obvious. And a question like the first question on your learning goal, you wouldn't even have to think about it. It would just be like second nature to you. But we're not there yet because we've just started working with this a few days ago. So the closer you can get to the point where if I ask a question and you just immediately know what it's talking about, what property it's referring to, how you're going to solve it, that's where you want to be. And we're going to look at some of that today in some of the different examples that we're going to do. If any of them catch you by surprise, you really, really want to practice to the point where you've got it. Because sitting and trying to figure it out during a test is never a good practice. To be honest, though, probably the hardest thing we're going to do today, at least for me, is drawing 3D vectors. I don't know about you, but I find it very difficult, so I'm going to give it a try. It's not something that we're going to ask you to do on a test. There are a couple of questions. I would encourage you to try them, but if you find it hard like I do, don't stress about it. Again, with some practice, you'd be able to. If you've done any art or any perspective drawing, then you're probably going to be way better at this than me, and maybe you can give me some tips later on how to improve my drawings in 3 space. But anyway, so we've got a couple of vectors, let's say. So if V is a vector in 3 space, again, the standard is its tail is at the origin. It can be represented by its coordinates. So if point P is x1, y1, z1, then the position vector V would be from O to P. So again, using square brackets, all we're doing is adding a third coordinate, the Z coordinate, right? So and basically everything we do today is instead of working with 2 coordinates, we add on a third. But every formula that you look at would basically be intuitively scaling it up with 1 extra coordinate. So very little changes. Easy enough so far? So let's take a look at an example. Example 1, sketch the following 2 vectors, 2, 3, 4. So somebody remarked this morning about how Why did we move where the axes are? And I don't have a good answer to that, and I don't know that the standard is as solid that X is the one that's kind of coming out of the paper here. And like, why wouldn't you leave X here and Y here and change this to Z? I think sometimes some people do, and I don't know that it's as clear a standard. But anyway, this is the one that we're going with for now. I would say, I mean, you could use this if you ever are sketching it for yourself, but you also just label your axes would be important. The only advice I can give in drawing these, draw out a little box with some dotted lines, and when you're first we have to make a scale, and then when you're making the box, just try to make your lines go parallel to the axis that it's like going with. Okay, so think about sticking parallel. So I'm going to start with my scale. 1, 2, 3, 4, 5. 1, 2. This one's all positive, so I can go out on the dark lines. 2, 3, 4, 5, and 1, 2, 3, 4, 5. All right, so now I do my box. So if I'm going out 2 for the X, I go out 2. And then I'm going 3Y, so I'm going 3Y, and I'm going to make this parallel and parallel. See what I mean? So I came out 2 and out 3, and then I'm finding where they meet out in 3 space. 2x, 3y. Then I'm going to go up 4z. So 1, 2, 3, 4. And again, I'm going to go out. And just kind of finish my box. I think I have all the lines. Okay, now ready? So again, you can kind of think of it this way. 2x, 3y, 4z. So I've gone to this point, haven't I? 2, 3, 4. Do you see it? And there's my vector. Software these days can do a very good job. I'm not sure Desmos can, but GeoGebra can do 3D vectors, and Wolfram Alpha, I think, can. And I've seen apps. Emre, you had an app, right, that did 3D stuff. And you can like rotate and look at it from different angles. Very useful. I mean, we're representing a 3-dimensional concept in 2 dimensions because we're doing it on a screen or on a piece of paper, which for all intents and purposes is 2-dimensional. So it's tricky when you think about it like that. But if you draw this box and you do it correctly, which I'm not really sure, again, like I'm the best at it, but you can get the perspective that the arrow is kind of coming out 3-dimensionally. Just like drawing a box in 3 dimensions can look sort of like a 3-dimensional box, even though it's on a piece of paper. Okay, and this one's even harder because it's got a negative. Somehow I always manage to mess this one up. So it's a negative 3x, so I'm going back this way. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, here we go. Let's try it. So I'm going back 3 and over 2. And up 4. Aha, not bad. So if you want to watch, I go negative 3, I go over 2, and I go up 4. to this back corner. Small things excite me sometimes. What? Okay, so -3, +2, +4. And there's my vector. Kate, you don't like it? Why? Yeah, I know. It's hard. Anyway, not a big deal. It's not something we're going to do a lot of, but again, I would challenge you to try it. Just focus on the box. Focus on staying parallel to the lines. It's worth trying. Isabel? No? All right. Let's move on. Again, the unit. So we talked briefly about the unit vectors. There were some questions about these unit vectors in two space, like in the practice. And if you had not heard about what the capital T unit vectors are, as opposed to a unit vector, you would be like, I don't know what this is talking to. So a lot of this, because it's new, it's just new notation and like speaking a new language, you just have to learn some of these definitions. What are the unit vectors? Well, they are I hat, which is 1, 0, 0. 3 space, so we always have 3 coordinates. J hat, 0, 1, 0. And what do you think the third one is? K hat. So this is what I mean. Almost everything we do today, except for maybe drawing 3D vectors, is like exactly what you would expect it to be. Do we just go up one letter to K and put a hat on it, and then the 1 goes in the Z spot? Yes, exactly that's what you do. Okay. The unit vectors are easy to draw. So here's I hat. Here's J hat. And K hat. Again, this is not something that we are going to use a lot of. It's just a definition, but it's a definition that would become important if you continue to pursue more in vectors and linear algebra, which many of you will do. So you are very likely to see I hat, J hat, and K hat, and you will use them. And if we're lucky, we're going to talk a little bit about matrices in this unit, or sorry, not in this unit, in this course, because we're going to be done a little bit early. We're going to have a few extra days, so we're going to put a little extension on the course, not part of the regular curriculum, but for anybody doing linear algebra. So we'll talk about matrices, which is related to vectors and linear algebra, and we might see them, we'll see when we talk about those, because that's where they start to come back up. It's just not a big part of this course. Okay, and so if I had vector v, which was x1, y1, z1, if I wanted to write it out in its 3 coordinate components, it'd be 1, 0, 0 plus, sorry, that's not right, x 1, 0, 0, 0, y1, 0, and 0, 0, z1, or x1 times I hat plus y1 j hat plus z1 k hat. Same as we've done before, just the third coordinate. Okay. Like I said, we're basically going over everything we've done, which is a nice review. but now just in 3 dimensions. What about magnitude of a vector in 3 space? Where did the formula for magnitude of vectors in 2 space come from? Seema? Very good. Pythagorean theorem. What's Pythagorean theorem in 3 space? So this one's interesting because I think it's not intuitive, and in fact, I think it would surprise a lot of people that it works out this way. But it's not too hard to show. We could show it. We're not going to, but we could show it relatively easily, or you could, I'm sure, Google it, look it up, and see an easy derivation of this. Turns out, it's just this. Like, I think that's surprising, that Pythagorean theorem scales up like that to 3 space, but it does. Well, we don't call it Pythagorean theorem, but turns out it works out like that. So again, it's pretty easy to remember. Okay? Okay, so a couple of examples. So given some vector u, write it out in terms of the unit vectors, I hat, j hat, k hat, and find its magnitude. So it's just going to be 2 times I hat minus 1 times j hat, so minus j hat minus 3 times k hat. Like, that's how easy it is, right? Magnitude of u, 2 squared plus negative 1 squared plus negative 3 squared. And I believe that works out to root 14. 4 plus 1 plus 9, 14. Okay. What about scalar multiplication? Again, it's exactly the same. So if vector u is u1, u2, u3, then k times u is k times u1, k times u2, k times u3. This is what I mean. Like, everything basically just works out this way. You just have another coordinate, so you do it the same, but with another coordinate. Now, these 2 next examples are not ones we've done. I think there may have been one in the practice kind of like this somewhere, but if not, or if you didn't do the practice, we'll take a look at an example together now. So find the value of b. I've got 2 vectors, 1, 2, 3, and 5b, 15. Find the value of b. That makes the 2 given vectors collinear. By inspection, what do you think b is? No. 10. So if I multiply 1 by 5 to get 5, I got to multiply 2 by 5 to get 10, 3 by 5 to get 15.